Thank you for coming on this very dreary day. So, review. When using the method of formal power series, so a pretty formal method showed that after a biholomorphic change of variables, and we wrote it in the notation W equals W of Z. It follows that F of W equals W to the K for some K, which is the order of vanishing of F as 0, whenever, of course, this automatically means this is 0, 0, so F of 0 is 0, and if you like, F is not identical. So if F is identically 0, it's something crazy. So we showed that. I wanted to point out that you can use formal methods quite often. And today, what I'd like to do is complete the analytic method. The analytic proof of this. And when you have something, I should mention what the tools are here. So the tools are the complex exponential map, complex logarithm map, whatever that means, and the holomorphic inverse mapping theorem. Which was implicit in this formal approach. In that context, the word biholomorphic is important. So, important to understand what that means. So a local, what does it mean locally biholomorphic? I think this is implicit or even explicit in what I've been saying. So locally a biholomorphic map, say, phi equals phi of z from the z-plane into the w-plane. So that's the picture we have here, and I'm going to scale it. It doesn't matter. I can assume phi. Here's the z-plane, and here's a w-plane. These are just two copies of the complex plane, and there is a map between them called phi. And I assume phi of 0 equals 0, so we can always organize this. And biholomorphic means what you think it means. it means that the map is locally biholomorphic in the neighborhood of 0, means there's a neighborhood of 0, U, which is mapped onto an open neighborhood V of 0, because phi of 0 is equal to 0, and there is a mapping phi inverse, which is also holomorphic, so that phi inverse of phi doesn't matter, we're happy to see. Okay, is that okay with everybody? Locally biholomorphic at a point, it means it maps this point to some other point, but we can call this point 0, it doesn't matter. It means that there's a small neighborhood, maybe a big neighborhood, a neighborhood of 0, U, in the domain space, neighborhood of V of the image space. This map is a homeomorphism of U onto V, and its inverse exists. It's a homeomorphism, but both maps are holomorphic.
Do you miss the identity? The inverse composed with the map is the identity?
Oh, well, there I go again. I don't know the difference between 1, 0 and the identity. So this is the identity either on U or V, depending how you look. I'm sorry. Maybe that was what also Nick was worried about. Or you were asking some other question?
Well, another question.
What was your other question?
Can you explain what the differences between doing a change of coordinate and a change of variable? Because they kind of seem related or pretty similar.
I think it's a good question because it means what is a variable. Yeah. And if you define a variable to be a linear coordinate, in this case, the linear coordinate, which I said z, or the linear coordinate w, then the coordinate and variable in my language are the same thing. Okay. But you see, as we, it's really a question: what are the giants of the past mean by the word variable? And I would like to define it the way I just did, but it can be very formal because, as you see, it can be big Z in the formal power series ring. So it's just some symbol, and in the minds of the giants of the past, I really think they were thinking this is just some symbol. And then by the way, this is modern mathematics too. Those of you, right? So it's just a symbol, and then you can evaluate the symbol some way you want. Right? So this is, in some sense, modern algebraic geometry as a point of view. Okay, some symbol, and you can evaluate this symbol any way you want. Right? So we proved that formally, and now we proved that formally, and now I'd like to give the analytic proof. And step 1 is the exponential map, understanding the exponential map. And the property 1 was, well, definition, let's write it down again. X maps C a priori into C is just a holomorphic function, has a power series development, just now equal. So in this variable, you say into the variable Z, but I mean in the linear coordinate Z, you just take, for each value of the coordinate Z, you take the power series expansion, you get some number. But the expansion is just some object like that. And these coefficients, everybody in the room knows these coefficients. And they die out very quickly, so this converges on the complex plane. Now, this formal stuff can be done over any field. So you can replace the complex numbers by something else. You don't care what the coefficients are. You care there's a field. And if this is a finite field, well, you know some finite fields, for example, FP, right? If this is a finite field, there's some huge danger, particularly, except in the complex of real numbers, there's some astronomical danger with n factorial being 0, right? In some field. Right? It could be 0. Okay? So this really works for the complex numbers, and that's all we're dealing with here. So keep that in mind. It's a very important map that exists for the complex of real numbers, and has the basic property that I wrote down on the blackboard last time. It is an X, first I'll write the property, and I really, well, it's my craziness that instead of just writing C and C star, which is the multiplicative group of the field C, yeah, and this is the additive group of the field C, yes? So that I'm writing here groups. You understand what I mean? Additive group that has an inverse A minus B and so on. I mean, you understand a multiplicative group here. And I'm emphasizing the fact here that we as adults say this thing should be a homomorphism of groups now in every sense of the word. C as an additive group, I don't care how you define it, is an algebraic group. Everything around here is algebraic. I mean, come on. I mean, whatever the definition, you don't even need to care about the definition. Whatever the definition is of algebraic, the operations here are algebraic, right? And C star is a multiplicative thing, group. Whatever the operation is just multiplying two things together. I mean, come on. Right? Everything is algebraic. But please notice, the exponential map is not algebraic. So it is some phenomena over the complex numbers, the power of complex analysis actually, that you have these algebraic groups over C here where you have this exponential map which connects them, and it's a homomorphism. It means, homomorphism means phi from G1 to G2 is a homomorphism of groups. A group means that, of course, phi, when you take, and now when you're doing group theory, you don't write the operation in here, you just put multiplications on it. Equals phi of G1, G2. Homomorphism means it transports the one operation into the other. In this case, it's a homomorphism of addition into multiplication. And here that means that x, I'll write it in complex numbers of z1 plus z2 is x of z1 times z2. And the proof of this fact is you fix z1 equals, say, x1 in the real numbers, and let z2 equals z run in the complex number. We use this slang, run in something, quite often, right? Let it run over there. Okay. And you prove then that x of x1 plus z equals x of x1. times x z. And let me say the final examination is here, an oral examination, and we'll make dates for the examination that are convenient for everybody. But let me tell you, if I ask you, why is the complex special map homomorphism, you should say, or in the following way, you should say we fix the first thing in the real numbers, and let the second thing run in the complex numbers, and apply the identity principle, because this holds for the second thing running in the real numbers. So you just say identity principle. You must, if for example, you watch me talk to a colleague, we will talk like this. We don't say some detail that I learned in some or I proved in my own papers. I make big jumps. It's let the first variable run in the reals and then apply the identity principle. That's, yeah. You need, yes.
So by homomorphism you mean the operation of multiplication can be separated into two.
This is an explicit statement, and this is the abstract statement.
So it can be addition, not only multiplication.
I said that, but I didn't write it. In group theory, we get tired of writing the operations plus, times, x, y, star. We don't write any operation. So this could be whatever the operation is in the first space, and this is whatever the operation is in the second space. You just have to get used to it, okay? We never write the operation, unless it's important. And here, of course, it's somehow, it is important, we're using it. So it's identity principle, it proves this, and now fix z, and again apply the identity principle to the first argument. Fix z and c, and apply the identity principle to the first argument. So that proves this fact, which is, maybe we call this proposition. It's important. Yeah.
How would we then show that it holds for two arbitrary complex numbers? Because so far we only showed the combination.
Very good. So he's asking again the good question. Yes, there are two questions here that need to be asked. First of all, I wrote up there from C to C star. C star is the multiplicative group, right? So that 0 is not in that thing. So the first thing we have to check is that 0 is not in the image. It really goes into C star. That's my version of your first question. And the second question is, it goes to every point in C star, so the surjectivity of the map. Yeah? That's what your question is.
It was more that if we, well, so far we only always had x1 being real and the second one, z1 being real and z2 being complex, or the other way around.
Yeah.
But we have not shown it for two numbers being complex. Well, I guess it doesn't matter.
No, it doesn't matter. It's symmetric. So yeah. So it holds for the second being complex. And not, okay. So I fix that second one complex.
Right.
And it holds for the first one being real. And then I do the same argument again.
Yeah, I suppose we can always split up the sum of two complex numbers into a real and complex part and then...
Well, absolutely. Implicit in all of this is that a complex number is the sum of x plus iy.
Okay.
Yeah. Okay? So that's the proof of that, and then there are two steps that we really want to prove. So a key fact that we really want to prove, and this is not so hard, is the image of x is contained in the multiplicative field. I mean, you can't imagine there would be anything else other than that, because, I mean, it's multiplicative, right? Right? Well, proof. If x of, say, some particular point, z0 equals 0, then x of any z, which I write as x of z0 plus z minus z0 equals 0 for all z. Well, I split up this thing, and it follows for all z. So this is almost a formal point, just using the homomorphism property, what we're talking about there. And so, of course, I can split up I can split this up here using the homomorphism property. So that's good, that at least it lands in CC. And then the second key fact is that X as a mapping, this is what he was asking about, does it take on all values, is surjective. We'd be happy about that if it's surjective. We believe it somehow or another. It should be if it's just somehow transporting anything here by addition to anything here by multiplication. You certainly hope that it should be surjective. Okay. And in my mind, this is a deep remark. This, I think, is a deep remark. So I will postpone the proof until 5 minutes and explain another key fact here. And that is the following proposition, which makes everything go here. X, by the way, if you're writing manuscripts, don't do what I just do here. Don't ever start a sentence with a symbol. You will just have experience to see that that is bad. So you get around it by saying, let x be the complex exponential function Oh no, I'm just practicing. You see, that's the nice thing about having a computer. You practice. And then you get efficient. The complex exponential function, exponential map, exp map, x. It's always good to write it again from here. C to C star is locally bihomomorphic. Locally bihomomorphic. That's why I was so precise here about what does it mean by locally bihomomorphic. I don't know where I talked about it. You would be, oh, here. That means given any point, there's a neighborhood of that point, which actually we will be able to really see, which is mapped by the exponential map homeomorphically onto a neighborhood of the image space, and the inverse map is holomorphic. It's perfect in the setting of holomorphic geometry, the perfect mapping in the setting of holomorphic geometry. It's locally bihomomorphic. Yeah. And the reason I say that I think that this is a deep remark is that the proof, which is in my opinion the only proof possible, uses the inverse mapping. So So proof will use the holomorphic inverse mapping theorem. And you've seen that in the formal proof because you've seen the formal inversion of a power series, and that's an inverse mapping. So we saw this, we observed this. In the formal proof. When we had Z equals, I can't remember the notation. I don't know. Z equals, oh, I know, R of W. Yeah? Then there's a formal inverse, R inverse Z of W. There's a formal inverse of just inverting the power series by a recursive formula. And this will be, this is a convergent thing, so this will be the way we get inverse mappings. Okay, so you can prove this theorem, if you wish, by formal methods. So our proof will use our analytic proof uses the real inverse mapping theorem. Which you know from calculus or whatever here. So, in real inverse mapping theorem, and I want to emphasize, is valid in great generality, which you will see. So, in higher and in fact, in some sense, in infinite dimensions. So, here we're in dimension 1. These formal power series methods are very trivial in dimension 1 because there's only one variable. But in more variables, whatever variable is, formal symbol in this case, it's very, I was talking to Kayvon last night at dinner, just thinking about formal power series ring in two variables and trying to prove what we call the Weierstrass preparation theorem in two variables. It's the first theorem you would prove, the analog of what I'm talking about here, two variables. It's very difficult to do. So the formal proofs in higher dimensions are harder. So we use analysis. Okay. So let us recall, if you have a mapping from Rn, and this is my notation, that means a locally defined mapping in the neighborhood of 0 in Rn. Okay, so it's very convenient. Here's some neighborhood of 0 and here's Rn. And you have this mapping phi, and here is a neighborhood of 0 in Rn. So, and it's the same setup as over here, some local neighborhood here, some local neighborhood here. Yeah. And you want to ask the question, when is this map invertible? And so you want the inverse map to be differentiable and so on. And so this map should be differentiable. And maybe even more. Maybe even, you have to think about it, C1, and continuously differentiable. There's all this delicate business here. So you need to worry about this always. What you need here is a local diffeomorphism. That there's some neighborhoods where this thing is really has a differentiable inverse, as I talked about in the holomorphic setting, local diffeomorphism, if and only if the Jacobian, the differential of phi at 0 has rank in, well, it's from Rn to Rn, so it's, the differential is in GLN R. I.e. is an invertible, is linearly invertible. You should get the flair of in mathematics. You attach to a mapping its linear part, and you ask if the linear part is good, is the mapping good? Yes? You say if it's linearly invertible at the level from 0 to 0, that is actually a mapping of the tangent space. If that mapping at that level is good, and best means this in the case of n equal n, that means invertible. That's a matrix here because we have coordinates. Yeah, it's a matrix. This matrix is has a well-known name. It's called the Jacobian matrix, right? So if the Jacobian matrix, so this can be regarded as a matrix. And I like to write this if phi is given by functions f1 through fn. So it's given by smooth functions. This is a matrix in my notation of column vectors gradient f1 through gradient fn. I will ask physics people if you like the gradient being a column vector or not. It's canonically a one form, so I think it should be considered a column. Okay. Yeah. So this is matrix. So if that thing has maximal rank, which is in this case n, it means it's invertible. So if and only if the determinant of this matrix is not 0, Jacobian of phi at 0 is not 0. Quite often you see that as the condition, and that is a stupid condition because computing a determinant is a horrible thing to do. It's a highly nonlinear operation. It's just that the mapping is maximal rank. So when you have one of these things, then you have the theorem. Then you have the theorem. And you all know. But in my mind is a rather deep theorem. Did I state it? Oh. No, you did not state it. Theorem. The mapping phi is a local diffeomorphism if and only if the linear part of phi at 0 is a linear isomorphism. Anytime you're doing mathematics in a highly nonlinear situation, stand back and ask yourself, what's the linear situation? The linear situation is the linear part. The linear part of a map, I've written and discussed it there, and you understand it very well. So then you ask yourself the question, which all of you know, I'm getting, I will send my comments on your good questions. I will write my comments when I'm going home in the train and send them to you either tonight or tomorrow. You're making good questions, and you would ask the question here immediately, what is the linear part of F as a map from C0 to C0? Which is homomorphic. No, a complex linear map. No, complex. This is a complex map. A complex value map. A complex value map. Okay. Well, just for fun, let me prove that I can compute. One of my great teachers, I was very lucky to have some very wonderful teachers, told me the best mathematicians are the laziest, who don't like to compute and rather think. Unfortunately, you have to lock yourself in a closet sometimes and compute until you get it come out. And so let's compute this. And so we write F as a mapping from R2 locally at 0 to R2 at 0, local map. So F of xy equals u of xy in these variables again, I v of xy. Every place in the world uses u and v there. I don't know why, but this started with Cauchy probably, and it didn't stop. So that means that the mapping is just xy goes to u xy v xy. Right? And so this in the notation above, in the notation above, this would be F1 and F2 in that notation, right? The two things that define the mapping, right? And so the differential matrix, so the linear part is as a matrix in the standard basis here is gradient F1, gradient F2. That's gradient column vectors. So this is, gradient is first the partial with respect to x and then the partial with respect to y. So this is partial u with respect to x. And then we get tired of writing partial, so we write ux and uy. And here we write vx and vy. It's a matrix, 2 by 2 matrix. Right? Okay. So there. That's interesting, but let's see, assume that the Cauchy-Riemann equations hold. And so this is ux, and this is uy is equal to minus vx. So let's put it here, minus vx, vx. I use the Cauchy-Riemann equations for F homomorphic. And now, in this case, it is amusing to write the determinant of that equation. So the determinant of the linear part equals ux squared plus vx squared. There are all sorts of, that's very interesting, right? That's really very interesting. Or, by the way, if you look at it, it would be the same in y. I mean, x, it's very amazing, right? Some sort of norm here. Very interesting. And in fact, if you look what this is, it's the derivative of the function as a complex function, right? Where f prime, in my notation before, is df dz. And that's what that is. You just check. That's a little remark that you just say, if you have a local holomorphic map, F, mapping 0 to 0, if you like, is a local diffeomorphism. If and only if its derivative in the above sense is not 0. That is wonderful, isn't it? I mean, you just, it brings the whole picture of the Jacobian and all of this stuff into complex analysis. Right. You're not surprised because you know that means that f of z, now in this variable or in the formal variable, I don't care. Let's say its derivative is equal to 1, I don't care. Well, let's write it here. It's f prime, let's write it here. F prime of z there plus higher order. And you saw in the formal argument, I called this thing w. If that were a big variable, that would be w, and it was key that this highest order term does not vanish. And then you can invert the power series, and the mapping is invertible, but inverting the power series. So you're not surprised. Okay, that's great. Now, the claim is the inverse mapping, which you know exists and is differentiable, is holomorphic. So this is a standard thing. Look what you do. Another thing you do, you get a formal inverse, like as we did yesterday, and then they prove that if the mapping converges, then the formal inverse converges. Here you get a smooth inverse, and prove if the mapping is holomorphic, then the smooth inverse is also holomorphic. Okay. So you should draw a picture. Z-plane, if you like. You have the mapping F, and you have the W-plane, if you like. And you have a mapping G to the complex number. Okay, I don't know. No, we have mapping G back to the Z-plane. Okay. So we know that, I think I want to do it this way, I'm not 100% sure. Yes, I think I want to show that G is holomorphic. And what I want to do is so show, so here's what we have here, that F composed with G equals, now I pick, G is either Z or down the I don't know, depending where you are. Right? So just for fun, let's look at F. Let's look at G composed with F of Z. Just for fun. Okay. And just for fun, we know what that is. We don't have to be a genius to know that that's equal to Z, because it's the inverse map. And now, just for fun, let us compute the derivative of that. Well, let's compute, this is, I'm calling this the left-hand side, and this is the right-hand side. So it says that the derivative with respect to Z bar of the left-hand side is equal to 0. We know that because that's Z. Right? Hope this is going to work. Otherwise, I have to turn it around. I'm not sure. I think this could work. Let's watch it. So now what we need to do is compute the derivative with respect to Z bar of this thing, G composed with that. Right? Because we know it's 0, and we have to understand what this guy is. Now, when you see that, you see the chain rule forcing you right in your face. Right? It's called the chain rule in 2 variables or higher variables, and we've never sat down and checked out the chain rule. Right. So, chain rule. Now, if you apply the chain rule here, you will see that this implies that the partial of G with respect to W bar is 0. Okay? You will see that implies that. And that implies that G is homomorphic.
So you pick like some Z or any Z? You fix the
Z is a variable here. So I'm taking the partial derivative with respect to Z as a variable.
We assume F non-constant, right?
Hmm?
F is non-constant.
F could be constant a priori, but it's not. We know its derivative at the origin doesn't vanish, so F is highly non-constant. Okay? I mean, it's a question. I understand your question. This is a differential operator. These are differential operators. These map functions to functions. Okay? That's what I mean by this. Okay?
I just confused like G of Z is like some kind of fixed point or
No. There's no point. There, I know what you're saying, but again, let's go slowly through. It's very good to pin this down, what he's saying. We have a map, I called it F. Okay? It maps an open set onto an open set, and it has a differentiable inverse, I called it G. Okay? Those are mappings. Okay? I regard them as holomorphic functions. Okay? I'm lucky in this case because a holomorphic function maps something in R2 to R2, thinking of it as a complex map. Okay? I regard them as functions, and now I can differentiate these things as functions. These are the basic differential operators of complex analysis. D with respect to Z, and D partial with respect to Z, and partial with respect to Z bar. I'm differentiating with functions with respect to those differential operators. Okay, I just want to remind you, in case you've forgotten, dz, for example, dz bar, for example, is 1/2 dx plus I dy. Okay, and when you saw that that's dz bar. When you saw that in real analysis, it didn't bother you, and so it shouldn't bother you now. Okay? So these are partial differential operators. Just a comment, and I'll answer your question. Virtually all of you are either have heard the course on calculus on manifolds or are taking it now. If you look at some operator like this at a point, this is what you're talking about at one single point. That's the partial derivative of the function at that point. Okay? That is an operator which is called a tangent vector. So in two variables, a tangent vector at a point always looks like A partial at the point, evaluated at a point, B partial evaluated at a point. That's a tangent vector. So you're taking a partial derivative in some direction. That's what you're thinking about and getting, and the answer you're going to get is a number, because you've done it at a point. However, if you let the point run, that means you have this tangent vector going all over the place. We call that a vector field, right? And then you differentiate functions without the point, and that means you differentiate a function and get a function. And that operation is differentiating in various directions depending on the point. That's why we call it a vector field. So if you like, this is some sort of vector field. Okay, but I think for this course it's a differential operator. It's just differentiates functions, you get a function. Does that help a little bit?
Yeah, but like g of f of z cannot be always equal to z, right? Can we...
Of course it is, because G is the inverse mapping. Maybe I didn't say this, I said, the inverse mapping, I want to prove that the inverse mapping is holomorphic. The inverse mapping exists, but it's a big jump. You've forgotten it because it's a big jump. It exists because of the inverse mapping theorem over the reals. The inverse, yes? The Jacobian of this thing as a function of real variables is non-zero. So that means the inverse mapping exists. And now we have to check the quality of the inverse mapping. Okay? Yeah.
I didn't really understand how the chain rule really helps us, because it just gives us a product where one of the components is already zero.
Let's look at it. Okay? So what is the chain rule? I think it's a very good exercise for you to do a little bit of the calculation here, but let me just say what the chain rule has to be, and maybe not even and tell you how you prove it. So if you have any f of z is equal to partial f z at let's say at a point, times z plus, just in general, Nico, and I'm just writing down the chain rule in general, okay? Z bar z plus order 2 terms. Order 1 smaller than order 1 terms, small o, right? So, and g of w equals partial f with respect, g with respect to w. Say we're doing it all at the point b, w plus partial g with respect to w bar plus small terms, order O. Okay? So, what we have here is plus higher order, plus these higher order terms. So I write write g of f of z. Oh, not x. Yeah? Okay. G of f of z. Well, it's linear stuff plus higher order terms. Right? So you put what is this? Can you do it in your head? You put in here w equals f of z. Right? You put in here w bar equals whatever it is. Right? You put it in. So this is equal to partial, if you write it down, partial of z with respect to z, f of Do you remember the chain rule in two real variables? Have you ever seen the chain rule in two variables? I know some of you, yeah? Well, you know, do you know the proof? I forget the chain rule, but I have to prove it every time. Okay? So you're applying G to this terrible thing. Right? Right? You're applying G to this terrible thing. That means you apply the linear part to this terrible thing. Right? Plus you apply the higher order stuff to this terrible thing. But the higher order stuff in the Taylor series of development of this is going to give you higher order stuff. So you're going to write this plus higher order stuff. And what you put here is a composition of the linear maps. You understand? This is a linear map, and this is a linear map. So this is the linear map, which this is the Jacobian of F, so this is the linear part of F. Linear part of F, and this is the linear part of G. And you make a composition. Okay? Okay? Yeah. So can we do this and not waste too much time? So what do you put? You put W equals this, and now I put, well, I'll put it here, G of Z W, 0 W, and now W is this, times F of D of Z of Z, plus, I have to put in W equals F of Z plus partial F. You see, I'm putting this in. You don't have to be very smart to put something in. You understand what I'm putting in, yeah? And I'm putting in that, and now plus partial of G with respect to W bar at 0 times, and now what is W bar? W bar is this, so it's partial this whole thing bar, Z, Z is 0, Z plus partial F Z bar plus higher order term. You get it? When you compose these two maps, you compose the linear part plus jump. Right? Okay. Well, this map is holomorphic, don't forget. I mean, I wrote the general chain rule down because you asked me what it was. Right? And I told you I forget it within minutes. You see, I'm walking outside to see a friend and I've already forgotten the chain rule. But it means, right? It means you have a linear part plus jump, linear part plus jump. The composition of the maps is linear part, and then compose the linear parts. When you put jump into the linear parts, you get jump. Right? Because the linear parts don't kill the jump. I mean, don't make it worse. So it's only that. This is the chain rule. Right? This is general rule. You have a map, from place to the other. The linear part of the composed map is the composition of the linear part. Okay. That's the general thing. Right? So you put it in here. And F is holomorphic in our case. Yeah? In our case, I wrote down the general thing. What does that mean, F is holomorphic? Well, it is aha, 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 aha. That's that. Okay. And now, I'm writing this map. I'm writing this map. I have to call this H of Z. H usually would stand for my last name, but this stands for the word horrible. This is right, this is some horrible thing. Right, this is H of Z. And H of Z is the partial derivative of H with respect to z, dz, plus the partial derivative of h with respect to z bar, plus junk if nothing counts. It's only linear. That's the reason linear algebra is one of the most important subjects in mathematics in the beginning. Right? This is linear plus junk. And now I really want to know something. Okay, so let's see here. So the dh, what did I want to compute? dz bar. That was the thing I had this great idea someplace, because I know that answer is 0 in this case. Right? Because f composed with g is equal to z. And this is 0 in our case. But what is it? It's the coefficient of z bar. It's the coefficient of z bar here. So it's dg dw at 0 times oh, ha 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 ha! The coefficient of z bar here is nothing, because this thing is holomorphic. Aha! So that's that. Oh, this is bar. This is the rest of it. Aha! d f d z bar. This is the bar here. Right? Isn't that what I just computed?
And why is it 0?
Well, I'll write it out to make you more happier. This is dg dw bar times f prime of z. Right? Oh, did I forget a bar?
Yeah, you're missing a bar.
Now, of course, I did the calculation at 0 to make life easy, right? But it's a calculation anywhere. It's a differential operator, if you like. Right? And it's the same calculation. If I have, everything here was 0, so this is the problem. If this is a mapping to P, and then this is a mapping at f of P, right? Here we had the advantage that f of P was 0, and, okay? So we put it in general, you're going to get this term.
Yes. And why is it 0?
Because it's the composition G composed of f of z, which is equal to h of z. On the other hand, it's the inverse map, this is z. So the derivative with respect to z bar is 0. You look mystified.
I don't know why I
You just take the derivative on both sides,
Yeah.
and then you get that the derivative with respect
Okay,
h with respect to z bar is 0.
let's go through the proof again. It maybe is I'm explaining
Oh,
clearly.
yeah, okay.
F is a map. G is its differentiable inverse. Yes?
Yeah.
F of z is I don't know what it is, but G of f of z is z because it's the inverse mapping. G.
Yeah, but, don't we then always say that the composition is holomorphic?
The composition is z. It's the most stupidly holomorphic that I know.
But don't we try to claim that G is holomorphic too?
That's what we want to prove.
Okay. I don't know why.
No. It's good to discuss that. That's the reason we have such nice small classes at Yahoo's. You start with F. Forget all this technical stuff. It's not important. Start with F. F is something I don't know what it is. It's holomorphic though. We use something and we find out it has a differentiable inverse mapping, G.
Yeah.
That means f of z composed with g is z. I understand what he's talking about is z as a function. It's the z. It's the linear function z. I mean, you can think of it as numbers also, but it's the linear function z. So g composed with f of z is equal to z. I take the d bar operator, that's partial derivative with respect to z bar, on both sides. That's what Uppig just said. The partial the derivative of, with respect to z bar of z is 0. Okay? So I get 0 on one side of this equation. On the other side of the equation, I have some horrible thing, h of z that I'm differentiating.
Right.
I applied the chain rule. And what I got with the chain rule was this.
So that product is 0. Okay.
So that is 0. But the derivative of f is not 0.
Ah, okay. Yeah.
Isn't that wonderful? The derivative, the coefficient that you get here, the derivative is nothing. Maybe I had said that. D bar G is 0. Maybe I had not said that yet. Okay. So that's the theorem.
Are these evaluated 0?
Hmm?
Is the partial derivative of g at w part evaluated at 0?
So that's what I just said. Thank you very much for making me repeat that. I did this whole calculation at 0 to make life easy. Yeah. However, the chain rule means, I just started to say, that you go from P to F of P, right? So you know this chain rule of real analysis. It's the same thing. Everywhere here you have F of P, and here you have here G at F of P. Right? You just have to keep track of what does it. But I recommend you always assume F takes 0 to 0, and it simplifies your notation immensely. And it's no change, because that translation doesn't change anything. Yeah. So after translation, you assume it goes to 0 goes to 0, and so you have this fact. You're okay now, right?
Yeah.
Isn't that amazing? It's beautiful, but you're using some very powerful tool, namely the inverse mapping theorem over the reals. And in my mind, that theorem is not deep, but is somehow a little bit deep. You use Banach fixed point theorem and so on. You use various analytical tools to prove that theorem. Now I would like, in the remaining 5 minutes, and by the way, thank you for your questions. They're all always very, very good. I always say that there are basically only 2 theorems for beginning real analysis. One is called Stokes' theorem, the other is called the inverse mapping theorem. We just use the inverse mapping. Okay. And now I'm going to prove the normal form theorem again using this technology. Okay, the first thing is so theorem 1, it's not a theorem, but I'll call it a theorem. If a local power series is a unit, then U is equal, I'm going to make you crazy because I just used U plus IV, right? That's terrible, right? So let me just say, if F is just a local power series, let's call it that, then F equals G to the n for any n. So any n. So to make this precise, then let me even make this precise. Then for every n in the natural numbers, there exists a unit Gn, so that f equals Gn to the n. Right. In other words, you have an nth root. Well, that's very easy because it's, in fact, I define Gn equals x of 1 over n del n of x. So I wrote this down the way I learned it in the 8th grade. Right? And everybody in the audience says, what in the devil is ln of f? Yeah. You learn it over the reals in the 8th grade, and we just talked it over the reals. But f is ln equals the non-unique, it's not unique, we will discuss this, local inverse of the x function. We will talk about this in great detail, but the problem is the exponential map is not globally biholomorphic. It's only locally biholomorphic. So that means that given some neighborhood about something in C star, we have a local inverse, but it's not unique because you have many inverses. I mean, you know this. This has to have many inverses because you have them plus minus the square root of 2. Right. That's an example. So you know that it has to be non-unique, but it is a local inverse, and so this statement is true locally, and everything I've asked for here is true locally. Okay. So if f of z, here we go. Okay, h of z, we know is a holomorphic function, which is z to the order of the whole of h is holomorphic. So h is holomorphic in the local ring is some vanishing thing times a unit, which I've just called f. Then this thing I can write as z times f to the power OH, and no, not f, what did I call it? Gn. Gn as above, where Gn, where O, the order of h is n. Right? I took the root. Okay. And now we get back to what everybody's asking here. I'm going to call this thing W. Right? But I can call that W after a biholomorphic change of coordinates because this is z times the unit, and since this is a unit, the derivative of what I have here doesn't vanish at the origin. So this is, okay, if you like, I will call it W of z. And now compute W prime of z at 0 is the leading term of g, which is not 0. Multiplication formula for taking a derivative. Right. Derivative of that times that times the derivative of that, but that kills the derivative of that, so I've only got the derivative of that times that, so what we've really got is just the evaluation of that thing as 0, which is not 0 because it's a unit. Okay? That means W of z, and now this is back to the whole question that I've been dramatizing for a week. W of z is W is now a new variable. Right? But what it is a mapping. Z goes to WZ is locally bihomomorphic. Because its derivative doesn't vanish, I use the holomorphic inverse mapping theorem. So that implies that F is equal to W to the order of F. That's it. Right? In that coordinate. Right? You see what you have done? You had here, you start out here in the z-plane, and you go over to the w-plane with the bihomomorphic change of variables. You transport your function over to here, f of w here, or f of z here, depending how you want to do it in this coordinate. You have to make change of variables. Here, f of w is w to some number, this order. Here, f, oh, it's not f, it's what? H. H of w is here, something good, and h of w here deserves the name letter H because it could be horrible. Right? You start with a horrible holomorphic function, whatever it is, you don't care, it's just not identically zero. Right? In the good variable, in the good coordinate, it's just w to the k, there's some number. Okay? So I don't know, you're talking to your favorite high school teacher, and he says, well, look, I have some horrible thing, e to the sine. I don't know how well can you, I don't know whatever you do here. I want to make sure that it's 0, 0, so some horrible function. That's horrible enough for the example. I mean, you could do it, right? Sine, you know the power series developed per side, you put it in exponential manner. You write down what everything, right? Z, sine starts with z. I killed the first order term of that by taking off the 1, right? And this is z plus higher order terms. If I've done it right in my head. I think I have, actually, right? And in engineering science, in physics, and every place else, nobody cares about higher order terms, except in mathematics. And I just spent a week beating you over the head of this stuff, and then I say this function, h of w, is w. Right? In the right coordinate. So you're doing mathematics up to coordinate change. And if the coordinate change is bihomomorphic, you are preserving everything in complex analysis. So you should do it. If you don't do it, you're done. Right? You preserve everything in complex analysis, make the coordinate change possible. Now, if you're doing linear mathematics, you better not do homomorphic coordinate change. Right? If you're doing, I see a question coming. No.
So what is our change?
Huh?
What is our change in variable? Do we say you replace?
I told you what you do. The change of variables is this is the change of variable. In this case, this function becomes the variable because it's bihomomorphic.
Oh, so the whole thing.
It becomes w. And
you're w of z plus 1 of z.
But in the new variable it's w. H of w is equal to w. I'm sorry. All of this crap that you get in, excuse me for using the word crap, but it's really correct in this case, that you hear about trying to understand some horrible function. If you're only trying to understand that horrible function in a neighborhood of 0, then make a coordinate change. My teachers from, some of these people were born in the 1800s, some of my teachers. They do that like that. Riemann did that like that. Everybody does it like that. They don't even think. Just make a coordinate change. Just say that function is w. Give me a break. Right? That's why we're looking for normal forms. Right? We're looking in every context for a normal form. What does it mean, a normal form? It means up to a change of variables, which is appropriate in the context. Right? This is really fundamental. If you are doing linear geometry, You look for an operator. You look for a matrix. And there's some terrible n by n matrix that some guy in computer science wants to invert. Right? Right? And if the matrix is a good matrix over the complex numbers, more or less generic, you say the matrix is diagonal. The matrix is diagonal. If it's a generic thing in the complex, even if you look at this, you look at a matrix, Aij, complex, n by n. And you say, I say, let's look at a generic one. Just take Aij generic. Yes. After a change of variables, this matrix is diagonal. So I say, I don't care which variables I use, I change variables. In my lecture yesterday and these things, I choose an appropriate frame. Yes? This matrix is diagonal. Yes? It means I can conjugate this thing with a good matrix that I like and make it diagonal. Yeah? And that's much easier, because conjugation is the correct change of variables. Right? That's the appropriate thing in linear geometry. Local biholomorphic mapping is the appropriate thing in complex geometry. Local diffeomorphisms is the appropriate thing in smooth geometry. Local homeomorphism, global homeomorphism. Yeah? It's very interesting, right? What are the normal forms? That is the only thing to think about at first. Right? Okay, thanks for your patience. Have a good week and keep up the work.